Alright, this is the third video in the quantum physics chapter, chapter 27. I think this is going to be the last one. I looked at the material. I think I can get it done in um, not too long of a video. I don't think there's a whole lot of example problems. It's more of going through some theory, and it may get a little bit longer towards the end. We'll see. So we had looked at the Niels Bohr's his model, which for right now it's pretty much one of the most accepted models. We do know it's not 100% accurate, but it still can be used as a way to do certain math and to explain certain things without having to go into the quantum model, which is a little bit different. And so, especially with massive objects, this model still applies. But based on this, we have, again, remember, you have N1, N2, and this atom, it could be any kind of element. So some element, we'll just call it element A, and it may have light coming down. I'm going to just give light, maybe I'll try that color. Let me do blue. And so you have light coming down. And with the light coming down, it has some wavelength, some frequency, which means it has some energy based on HF. And it will cause the electron, which I'm going to make the electron brown in this case. It's going to cause, let's say, this electron here to gain that energy, and because it's gained that energy, and if it gains enough energy, it will jump to this orbit. And so this is the idea of absorption. Okay, when this element is absorbing a certain amount of energy and making that jump, then we have over time where this electron will eventually jump back. And when it jumps back, I'll do blue again. It's going to release energy. It's going to release at a certain wavelength, certain frequency, based on the energy of HF. And at this point, this is what we will call emission. And so they came up with what's called a spectrometer. This is the device used to measure the wavelength of light using a diffraction grating that will separate the light into different wavelengths. This light's passing through a slit, and that is placed at the focal point of the lens. And the scope of the angle can be varied and measured. We have these in our lab. And we have different gas tubes we can look at. This is also something you can go to a museum and actually be able to look at. I know the Children's Museum in Lincoln County, I think it's called the Works. They have one where you can look through at the different elements that they have there and see the emission spectrum. And just what ends up when you look through, if you're looking at white light, so if you look at like the whiteboard or a light, you would see all the different colors of the continuous spectrum. If we heat up a gas, a specific element, we heat it up, which we have these little machines, and even in our lab, that heat this up. we will see what's called an emission spectrum, and you only see these certain wavelengths that are given off by that element. Right? And so they have certain electrons that have jumped orbits and are jumping back, and they're jumping back, giving off certain wavelengths of light. We can also do it looking through a cold glass, and what you see is actually the opposite. You see the absorption spectrum, what they actually have absorbed of the energy coming in. And so we use this, and this is one of the things we found has told us so much about different elements and so much about stars. So when we get into looking at the stars, what we have found. And so for the emission spectrum, this is very similar to what we have in our lab. Maybe not exactly the same. It's more of a box, but the tube looks almost exactly the same. You have a gas, and it's in this equipment that is used to heat it by providing electricity, basically. And the as the gas heats up, the electrons will start gaining energy and eventually jump to a higher state. And in this case, you know, we're not doing it by shining light onto it. We're doing it by actual electricity and heating up the electrons. But it works the similar way here. Instead of the light coming down into it, you know, we're sending energy into it through electrical systems. But anyways, the electron jumps up to a higher orbit, and then as it releases, and these electrons jump back down to the original orbit, it's going to release the energy, and you'll see the elements start to glow. And when you look through the spectrometer, you'll be able to see that the different wavelengths that are glowing. No, I'm not done. Go back upstairs. Right. Sorry, daughter wanted to ask me a question. And so this is sorry, it throws me off getting interrupted like that. This is how the emission spectrum will work, and how we start seeing these absorbed lines, which is usually how we see them if we go to a museum and look through these. They're always the heated ones. It's not as much information all at once, but it's really important information. And so what we have found that each element has its own unique spectrum that it releases, because each element has a different amount of electrons in orbits. And so for instance, copper here has 3 lines, magnesium here has a purple, a blue, a light blue, and what looks like some kind of greenish yellow. So like this unknown one, well, if we're comparing it to all of these, well, it has a blue line here. I mean, this one kind of does. This one really does. So it has to be one of these two. And then we see 3 blue lines. Well, that's 3 blue lines here. So it has to be this one, which means these have to match up too, and they do. So this unknown is strontium. You know, it matches completely, and it can't be any other ones of these. So when the sun is shining, or a star is shining, we can see what's being released based on what spectrums are coming in. It may release many different elements, but we look at what patterns are there that make up the whole of what's being released. The absorption spectrum, again, you don't see this as often in museums or whatnot. Light is shining on a cold gas, and it's going to produce the opposite. It's going to produce the absorption spectrum, what's being absorbed, and that's what's being released. The atoms in the gas absorb certain wavelengths of light and re-emit them in all direction. And so what is re-emitted will not show up in the absorption spectrum. So it kind of works in the opposite way of looking at it. Now, we get into certain series, and at first these may be kind of, um, difficult to understand, or seem more complex, but they're not really as complex as we would think. Um, you just have to kind of look at them and not get too overboard with them. And so first one is the Balmer series, which is these sets of black lines. And basically, this is using this similar formula we had, only instead of looking at the energy, we are looking at 1 over the wavelength. That's equal to R times 1 over, I'm going to call it N1 squared minus 1 over N2 squared. But this R now is a different constant. It's this 1.097. And that just comes from the fact that we have this now as looking at wavelengths instead of the energy. And the biggest thing with this Balmer series is it's setting this particular one, this N1, at 2. Okay, so it's looking at everything coming down to that second level. Okay, so it's not worrying about if it goes from 3 to 1 or 3 to 4. It's only looking at, 3 to 2, 4 to 2, 5 to 2, and 6 to 2. And it's looking at those specific wavelengths. And so we see that 3 to 2 ends up being 656 nanometers. 4 to 2 is 486 nanometers. 5 to 2 is 434 nanometers. And 6 to 2 is 410 nanometers. One thing to point out, these are all within the visible colors within this Balmer series. This Balmer series has found to fit hydrogen only. Within based on all the other ones, this is the one that fits hydrogen and works with hydrogen. The Lyman series, this one, instead it uses the same equation, so I'm not going to write it again, but instead of it being a 2, it sets out 1. It's looking from 2 to 1, 3 to 1, 4 to 1, and so on. And so what you see with the Lyman series is you see the wavelengths fall within this range here on the electromagnetic spectrum, and this is in the UV or the ultraviolet range. Well, again, the Balmer series was in the visible light. The Patchen series uses a 3. Level 3 is your final. And we see that these wavelengths fall within the IR spectrum. And so each one of these has a different region, which is kind of interesting how they separate out like that. And so if we go back up to that picture, we see the Patchen series again going to n equals 3. So 4 to 3 is 1875 nanometers. Then 5 to 3 is 1282, and 6 to 3 is 1094 nanometers, and then the Lyman series is 6 to 1, 5 to 1, 4 to 1, and so on. All following pretty much this equation here. And just setting this equal to another. I mean, we can do one where that's equal to 4 and it'd be a new series. We don't have a name for it though. Alright, so we're talking about electrons going from one energy level to another. We call this an energy transition. And then atom will emit a photon when it makes an orbital jump from a higher orbit to a lower orbit. And so we mentioned that before. This is more stable, and this is more unstable. And so as it jumps down, it loses energy and emits a photon. Some energy coming out of this atom. And this energy is going to be equal to that energy of the upper energy level and minus the lower energy level, which is what I showed you before with E equals RH 1 over N1 squared minus RH 1 over N2 squared. Okay, same idea. Each of these states is what we call a quantum state, and it has specific radius for each of these states. And this is where Bohr has came up with the whole fixed energy state. So if we think about it, if we have something moving about in a circular orbit, and this has a certain radius, and so this electron moving about has a certain energy based on the fact that it's a certain distance away. Kind of the whole centripetal force idea, mass velocity squared over this radius. And then if you go farther out, oops, you can just believe I drew that right. As you go farther out, you have a new radius. It has a new energy at this point. And so this is why, the idea was that these states were fixed positions with specific radius and specific orbits for these electrons. And from this, we have that the angular momentum then must be conserved. And so that angular momentum, remember, is going to be mass times velocity times the radius, based on what energy level you're in. So it's found to be the energy level times Planck constant h over 2 pi. And then the orbital radiuses we can look at these, and if we're setting if we look at this force here, this is the force between that nucleus and that electron. So we have Z being the number of protons times the electron, and then that one specific electron moving about. And this is the electric force. Electric force. Doesn't want to keep writing everything. So this is K, which is 9 times 10 to the 9th. And this is our radius of this orbit. And that's going to equal this force. That itself is the basis for this electron moving about, being within this fixed orbit. Now if we look at the linear, let me draw it on the white page. Let me get rid of this. We look at the linear momentum. Now L is mass times velocity times Rn. And that's equal to NH over 2 pi. Okay, we're going to square both sides. So when we square both sides, we get mv squared. There's a reason I'm putting these together. Rn squared. We didn't have to necessarily put these together in that step. then n2 squared, and then h over 2 pi squared. Okay, so all I did was take this side and this side and square both sides. As long as you're doing the same thing to both sides, it still remains equal. And then I solve this for n squared. And so I divide the mv squared over. And then if we notice, everything here is being squared. But we don't want to just automatically take the square root. I mean, that's not going to help us. There's a reason we're looking at this in this way. So we're going to multiply this out instead. And so when we do, we get n squared, h squared. And then the 2 pi will give us 4. 2 squared is 4, pi squared. And then mv squared. No, I'm feeling like I'm being a little secretive. The reason we're keeping this as r squared is because in the fourth equation it's r squared, and so it's a lot easier instead of having to take the square root and then re-square, just to solve this for r squared. And so we then take the force, the fact that it's equal to k times ze, which is the number of protons charge. It's the charge of all the protons in that nucleus, whichever nucleus it ends up being, and then over Rn squared. And that has to equal that centripetal force, mv squared over Rn. And so at this point, we can use the fact that our Rn squared is equal to this n squared h squared 4 pi squared over mv squared. And so the main thing we are wanting to do is figure out a way to link the radius with the radius prior. Right, so what we're going to do is we're going to take this equation up here, and we're going to take this equation here, and we're going to solve this equation here for that mv squared, which we have up here, which ends up down here in our equation. Now I didn't write down because I'm going to write in what we get. So this mv squared that not let me just make sure about this. I'm trying to see what I did here. Okay, these RNs cancel here. And then I messed up on my notes a little bit, but I correct it later on. I have to split up. I mean, this is mv squared itself. I have to split that up. And so I'm going to split up here. So I'm going to make this mv squared. That's what I want there. Because if you see here, there's an m here. And it's supposed to be there. I lose it here for some reason. I'm either didn't type it or I just, missed it. Alright, so this mv squared, if we divide this out, is just going to be equal to k ze times e over rn. And so now we plug that in for this here. That means everything in the bottom goes to the top. So you get n squared h squared rn over 4 pi squared m k ze times e. And so what we want to think about before we move on with this is what the R1 will look like. And for R1, your n is going to be 1. So you end up with just h squared on the top. And 4 pi m k and e squared. And so, and I'm leaving out a z for a reason here. But if we look at this, we have that here. We have the 4 pi squared, the m, the k. We have the n squared technically is taken into account for n equals 1, but I'm not going to. This one will leave. The h squared is there. And so if we look at that, and then we're taking in the e count, so we're leaving the z. We can put in R1 in place, so Rn squared here is going to be the R1, which in my notes that should be squared. R1 n squared over z. So this is the relationship. Let me write it more formal. I don't have it formal there. So Rn squared equals n squared over z times the R1. Alright, so let me clear this page. Let me check the time. This is the part where I thought things were going to start taking long. I wanted to see how much more I have left for this. we don't have too long left, so I may be able to finish this within probably the next, hopefully, 10 minutes. So if we look at energy level for an electron that's in orbit, it's going to have kinetic, it's going to have potential. Your potential energy is going to be, why is that? I don't know, I think my hand's on it, and that's why it keeps popping up. Your potential is going to be equal to a negative electron charge times the potential difference, which is going to be equal to the negative k z e squared over the radius. And then velocity, we can look at that from the angular momentum, mvrn, and that's equal to nh over 2 pi. And if we solve this for velocity, we get nh over 2 pi m times the radius. So this total energy we found is going to be kinetic, 1/2 mv squared, plus the potential, but the potential negative, so it would be minus your potential kz e squared over rn. And then we can plug in what we have for the velocity from here. This goes into here, and so 1/2 m nh over 2 pi m rn, and the whole thing's being squared because the velocity is squared, minus your potential. And then from this point, all these steps is working out the algebra, plugging in what we have for Rn, and moving through, and we get down to our energy equation that finally comes up with all these constants that's being multiplied by just z squared over n squared, which is the only ones that aren't constant. Okay, 4 is 4, pi is pi, k is 9 times 10 to the 9th. E is the charge of electron, mass is the mass of electron, and h is Planck's constant. And so all this comes to this negative 13.6 z squared over n squared. Okay, and this works for the hydrogen levels of 1, 2, and 3 within this total energy, looking at it in this way. Right, so the last stuff with this quantum mechanics and quantum physics, we know now that each n is considered a quantum number, and is related to some energy, and the lowest energy is when n equals 1, which we call the ground state, and the highest energy are considered excited states. Okay, for these electrons, they have more energy than they normally have. And so we have what's called stationary states, that the electrons are originally located in the lowest energy level that they can be. When we think about this is how we learn in chemistry. You have the first 2, and then you have the next energy orbit, and how many are in there, which I think is 6, and so on. Now we have what's called binding energies. And the idea behind this is that these bounded electrons have some negative energy based on how the potential is defined. And so it kind of goes back to this, let me go up. And you may have noticed, I wonder why, but we see that this energy is negative 13.6 times z squared over n squared. N is always positive. Z is the number of protons. That's always positive. And so, these electrons always have what's considered a negative energy. And so, the idea is, in order for these electrons to eventually have zero potential, they must get free of the atom itself. So, say this is the nucleus. So these are orbits. I'll draw a few. Potential equaling 0 is going to be out here. And these are all negative orbits. And we notice as z increases and n increases, that number is going to get higher. And so this first one's the negative 13.6. And so what it is kind of looking at is for these energy electrons to eventually get out, they have to gain energy. So they gain energy to jump up here, and they gain energy to jump up here, and finally they gain energy enough to get free. And now I have potential energy. And so that energy that they need is what we call the binding energy. And this is basically the energy needed to get away from the atom. And we're going to see when we get into nuclear stuff, to break a whole atom up requires some binding energy that these electrons, protons, and neutrons being put together actually has less energy, and we need to add energy to break it. And so the very last thing in all of this, we mentioned before that electrons have a wave-like pattern. When we look at these electrons, they don't actually have fixed states so much as having a wave-like pattern to them. So we see, they could be following the solid line, or they can be following the dotted line as they move about. And this is for n equals 5. It's a little different looking for n equals 3 and different looking for n equals 2. And how these patterns actually found is that they have to be able to have their wavelength make a complete wavelength as they move around. So for instance, I'm just going to draw a circle here. You don't want it to be where it comes up and goes down. I'm going to try to draw as even as possible, if I can, because the wavelength can't change. And then come in and not meet where it's supposed to. So this was the starting point, and this is the ending point. Okay, we can't have this. That's not what we want. We want it to match up completely. And so that's the idea with this. And we think about this as, electrons would be found somewhere within this wave-like pattern around this orbit. And if it doesn't complete it, then it ends up just dying out. Right? So the circumference itself must be some whole number of the wavelength. So we have 2 pi times the radius, that's the circumference, 2 pi r, equals some number n for the orbit times some wavelength. And so the wavelength equals h over mv from de Broglie's. So we plug that in for the wavelength and we get 2 pi Rn equals n h mv. And so when we manipulate this to get the angular momentum, we find that it's still nh over 2 pi for this angular momentum here. And so this is how the wave-like properties get placed into this model. But of course, it's still helpful to look at the fixed model as well. Alright, so this is the final video for, it's about 40 minutes. I didn't want to be that long, but it happens. But this is the part 3 of quantum. Next we'll be doing the atomic physics, which it's mainly theory. I shouldn't call it theory, but it's mainly some, I guess you say definitions, and not as much problems, so it may not be as long of a chapter. And then we'll get into relativity and then eventually nuclear, which that's, you'll probably hear me being more excited in those. I love dealing with that, and then especially with the stars in astronomy. Alright, I'll see you in the next video.